Okay. Thanks for the invitation and organizing this nice workshop. So I will tell you about a strongly quasi-convex PAC-Bayesian bound, which is a joint work with Nicholas Simon, Christian Igel, and Olivier Winterberger that we have presented a couple of months ago at ALT. So very quick summary of what I will tell you. So there are two major ways to convexify classification with 0-1 loss. The first one is to convexify the loss, and the second one is to work in the space of distributions over a hypothesis space. That's the PAC-Bayesian way, and the one we are taking. And what I will tell you about in this talk, so we propose a relaxation of the PAC-based KL bound by Ziegler, and an alternating minimization procedure for this bound. And we provide sufficient conditions for strong quasi-convexity of the bound. And when the bound is strongly quasi-convex, this alternating minimization is guaranteed to converge to the global minimum of the bound. Then we provide a special construction of a hypothesis space that works best for this bound that we have. And I will show some experiments where rigorous minimization of the bound was competitive with cross-validation and tuning the trade-off between complexity and empirical performance. So we didn't do any cross-validation of the parameters. We just rigorously minimized the bound, and we were able to compete with cross-validation. So I will start with very quick recap of PAC-Bayesian analysis. Many already talked here, so it's just to make sure we're using the same, talking about the same notation. Then I will show the strongly quasi-convex PAC-Bayesian bound, then talk about construction of a hypothesis set for this bound and some experiments. So PAC-Bayesian analysis works with randomized classifiers, and I will use rho to denote the distribution over a hypothesis class H, and a randomized classifier at each round of the game picks a hypothesis according to this posterior distribution, makes an observation X, and then returns the classification H of X. And I will use this expectation with respect to rho of the loss to denote the expected loss, and expectation with respect to rho of the empirical loss to denote the empirical loss of this prediction rule. Okay? Now this workshop is about 50 shades of Bayesian learning. I'm not sure whether somebody is counting the shades we are presenting here, but I will give you one more shade, and this is how I usually explain it to the students when I teach this topic in class. So when we consider classical learning, and classical learning we can see it as learning by selection. So if we have a hypothesis class and we have the best possible prediction rule, so when we select a hypothesis from a hypothesis class, there is an estimation error, or the variance, and approximation error. And when we select from a small hypothesis class, then the estimation error is small, but the approximation error is large. When we select from a large hypothesis class, then the approximation error becomes smaller, but the estimation error becomes larger. So selection from a larger class leads to a larger estimation error. What happens in randomized classification? So the idea is to avoid selection when it's not necessary. So when we have two hypotheses with similar empirical loss and similar prior, we take similar posterior distribution. And this way we achieve reduced variance at the same bias level. So this randomization, it allows us to avoid selection when it's not necessary and to reduce bias while keeping the same bias level. Well, just notation, so I'm using the big KL for the standard KL diversions and the small KL for the binary KL diversions. This was already said a lot of times today. And we have the classical PAC-Bayesian theorem by Matthias Ziegler. So for any prior pi over the hypothesis class and any delta in 0, 1 with probability greater than 1 minus delta over a random draw of sample S, for all posterior distributions simultaneously, we have that the binary KL divergence between the average empirical loss and average expected loss is bounded by this KL plus logarithm over n. So this was already in the first talk by Francois. The challenge is that this bound, it's not convex in the posterior distribution rho. And a common way to tackle this problem is to replace the bound with parameterized linear trade-off and tune this parameter by cross-validation. Okay? So even though we have a nice theoretical bound, most works end up replacing it with a linear trade-off and tuning this parameter by cross-validation. So I will show now something different. So we propose a relaxation of the PAC-based KL bound, which is based on refined Pinsker's inequality. And it says that for any prior distribution and any delta in 0, 1, with probability greater than 1 minus delta, for all posterior distributions rho and all parameters lambda in 0, 2 simultaneously, we have this bound. Okay? And it holds for all parameters lambda simultaneously. So there are some forms of, like, for example, Catonis bound, which is kind of similar, but it holds for one value of parameter at a time. So if we want to have it for more parameters, we have to make some additional constructions. This bound holds for all values of lambda simultaneously, so we can minimize it with respect to rho and also with respect to lambda. For the optimal lambda, this bound leads to this form. So we actually get so-called fast convergence rate. So when the empirical loss is small, this square root term vanishes, and we are in the fast convergence regime. When the empirical loss is larger, then we have the slow convergence. And this is, well, this is the same as like the bound in McAllister's 2003 work. So this relaxation is quite tight relaxation, which it achieves fast convergence rates if we want fast convergence rates. Now the nice point about this form of the bound, and well, we will denote by f of rho lambda the right-hand side of the bound. So for a fixed lambda, this bound is convex in the posterior distribution rho. And this is quite easy to see. So the expectation is linear in rho. The Kullback library divergence is convex in rho. So if we fix lambda, this bound is convex in the posterior distribution rho. For a fixed rho, this bound is actually convex in the parameter lambda, and it's minimized by this lambda. Okay, this is, well, quite simple test. The tricky point is that this bound is not necessarily jointly convex in rho and lambda. If it would have been jointly convex in rho and lambda, then alternating minimization over rho and lambda would be guaranteed to converge to the global minimum. But joint to convexity, it's not a necessary condition. So it's a sufficient condition, but not necessary condition. And in this case, we don't necessarily have the joint convexity. So we will try to see what can we actually say about this bound. And for this, we do a couple of simplifications first. So this is the bound that we had, and this is the optimal distribution rho given the parameter lambda. We can plug the optimal distribution into the bound, and then we get a one-dimensional function, f of lambda, which is f of this rho lambda and lambda, and, well, it's just the same function with rho lambda replacing rho. And so this is the first step in simplification. Now the second step, so we have this one-dimensional function, f of lambda, that looks like that. We have the posterior distribution. And now we are looking at the KL term. And the KL divergence term, we can, well, that's the expectation with respect to rho of lambda of the ratio between rho lambda and pi. The pi cancels out, so we get this expectation. And now we separate, so the denominator gives minus n lambda expectation of the empirical loss, and The other term gives this logarithm of expectation with respect to pi of the exponent. And if we plug this back here, then this term will cancel with this term, and we get that this one-dimensional function f of lambda can be written as this expression. Okay? And actually something similar to this you have also seen in Peter's talk earlier in the morning. So this is how the function, the one-dimensional function, looks like. And now we show the condition, sufficient condition for strong quasi-convexity of this function. So this is how a strongly quasi-convex function looks like. It has a single global minimum. So if at least one of the two conditions are satisfied for all lambda in the relevant interval, then f of lambda is strongly quasi-convex for the relevant lambda, and alternating minimization converges to the global minimum of f. So the conditions are that either twice the KL plus logarithm bounds n lambda squared n squared times the variance, or the expectation bounds 1 minus lambda n times the variance. Okay?
Can you tell us a bit about strong quasi-convex? It's not convex, but
yeah.
What is strong about it? What is the definition?
So a strongly quasi-convex function, that's, well, essentially a function with a single global minimum. So it's a function where every level set is above the function. So if you connect any 2 points, if you take an interval AB and you look at the value of the functions on an interval AB, the function is always below the line connecting f of A and f of B. That's
not just quasi-convex.
Huh?
So what's strong?
Strong quasi-convexity means that you have strong inequality and not. So if you are looking at the line from A to B, the function is strongly below this line and not on the line. So you don't have any plateaus in the function. Okay? What?
How are you doing your line?
So for any pair of points A and B, yes, you take the line between f of A and f of B, yes, and the function has to be strongly below this line.
But if I take, say, the minimum and very far to the right?
Yeah. It should be the level lines, not, yeah, okay, sorry. It should be the level lines that you are taking, and the function should be strongly below the level lines. Okay? So for any level line, the function is, you can't have a minimum of a function, kind of two minimums of a function between. So you have just one minimum.
It's just quasi-convexity with one minimum, right? Like quasi-convex, but also one minimum, and that's strong.
So you don't have any plateaus in the function, and for any level line, it's strictly below the level line. Okay? So a highlight of how we prove this thing. So what we show that so this is the function f of lambda, and we show that the second derivative of f of lambda is positive at all stationary points, which means that any stationary point must be minimum, and since it's a one-dimensional function, it can have only one minimum in this case. It's one-dimensional continuous function, so it can't have more than one minimum. And so taking the second derivative of this function, so the first derivative of this logarithm is actually the expectation of the empirical loss, and the second derivative is n times the variance of this loss. So this is where the expectation and the variance are coming in. So just a slide back. So this is, again, the condition is that the variance is bounded by either the KL plus the logarithm term or bounded by the expectation. Now this condition, it's not very easy to verify whether it's satisfied or not when we have a real problem. So we present a different sufficient condition, which is a relaxation of the previous one, and we call it weak separation sufficient condition for strong quasi-convexity. And I will first explain it with a picture. So we consider the loss of the optimal hypothesis in the hypothesis class. And the theorem says that there is a critical interval drawn here in red. And we more or less can have any number of good hypotheses, the hypotheses that are close to the optimal one. And we have more or less any number of bad hypotheses. The bad hypotheses are those which are sufficiently far from the optimum. And the key thing is to have relatively few hypotheses in this red region, which is neither very good nor very bad, but somewhere in between. And a bit more precisely, so if we have a finite hypothesis space and a uniform distribution, uniform private distribution over the hypothesis space, and for certain values of these parameters a and b, so if the number of hypotheses for which the empirical loss falls in this red interval is at most logarithmic in n over delta squared, then f of lambda is strongly quasi-convex and alternating minimization converges to the global minimum of the function. Okay. So again, some highlights of the proof of this result. So by the strong quasi-convexity theorem, if the variance is small and small, well, bounded by the two terms that we had earlier, then f of lambda is strongly quasi-convex. We look at the suboptimality gap of different hypotheses, so this delta H, and the variance can be bounded by expectation of the squares of the gaps, which is the weighted average of the squares of the gaps. And this posterior distribution, that's a Gibbs distribution that depends on the suboptimality of the hypothesis. So when we are close to the optimal hypothesis, the gap is small, so the contribution to the variance is small. When we are far from the best hypothesis, then the exponent is small, so again the contribution to the variance is small. And the critical contribution comes from this red segment where the gap is not too small and not too large. So we want the number of hypotheses that are in this red region to be relatively small. And that's how we get it. Again, I can go back a couple of slides to this first theorem. So what we essentially show is that this lambda squared n squared times the variance is bounded by the logarithm of n over delta squared. And we can actually ignore this KL term because it's always positive, so it only helps us to get even better bound.
Why do you do this alternating? Can't you do like a bisection search just on the lambda with the optimal p?
Like binary search on the lambda? Could also be possible, yeah. Okay, now I've shown sufficient conditions for quasi-convexity of this function. It's actually possible to break the quasi-convexity, so it's possible to construct an example where f of lambda is not quasi-convex, but kind of one has to work hard for it. So here is one example. So if we take 200 samples, delta equals 0.25, and we take exponentially many hypotheses, so 2 million hypotheses with suboptimality gap of 0.1 and a uniform prior, then we will get a function that's not strongly quasi-convex. But we have to take really a lot of hypotheses in order to break the quasi-convexity. And in all our experiments, f of lambda was actually even convex, not just quasi-convex, but even convex, even in the situations where the weak separation condition was violated. So it may be possible to relax the sufficient condition even further. So now the construction of a hypothesis set that we're working with. So the challenge is that the computation of the normalization factor in this posterior distribution can be computationally expensive. And if we do parameterization of the posterior distribution, that may break the convexity of the bound in the posterior distribution. So what we do instead, we work with finite hypothesis space. And for a finite hypothesis space, we can compute the partition function. But the point is that we need a powerful finite hypothesis space. So the next critical point is how to construct a powerful but finite hypothesis space. So what we do, we construct a sample-dependent hypothesis space where we take subsamples of size R. So we take m subsamples of size R each, and we train models on, so m models, each model is trained on R points and validated on the remaining n minus R points. And we look at the validation loss on the remaining points, and we adapt the bound so that the bound depends on the validation loss, and then there is the correction for the sample size that was used for estimating the validation loss. So this construction slightly resembles sample compression, but unlike in general approaches to sample compression where all possible subsamples are considered, we only consider m subsamples, which can be selected randomly, or they can also be selected deterministically. The main point is that these points should be subsampled independently of the composition of the data set. And a special case of this construction is k-fold cross-validation. So when we do k-fold cross-validation, we actually select, we train a model on k-1 parts of the data and validate it on the remaining part. But in our case, most computational advantage is achieved by inverse cross-validation. So we actually take small subsamples for training and large subsamples for validation. Okay. So now to the experiments that we have. So we compare kernel SVM trained by cross-validation to row weighting of multiple weak SVMs trained on d+1 samples, where d+1 is the dimensionality of the data. A bit more precisely, we apply row-weighted aggregation of these weak classifiers. So we look at the majority vote of the classifiers weighted according to row. But in our case, there was no significant difference between the majority vote and the Gibbs prediction rule. So you can see kind of both when you look at the graphs. A rough runtime comparison. So if we do k-fold cross-validation on kernel support vector machines, we have, so kernel support vector machines have super quadratic training time. So the training time is of order n to the power of more than square, and then validation is relatively cheap. So overall, the time for running kernel cross-validation on kernel SVMs is k to the n to the power of more than 2. In our approach, the training is actually the easy part because we are working with small subsamples, but the validation of the errors is the expensive part. And then if we take subsamples of size d plus 1 and we take m, which is of order n of such subsamples, then we get complexity which is of order roughly d times n squared. So we get an improvement in the power of n, which leads to computational speedup. And this is how it looks in the graphs. So what we have here, so the red line, that's the performance of cross-validated kernel SVM. The black line, that's the performance of our method as we increase the number of hypotheses, the number of those weak classifiers trained on small subsamples. And as we reach m equals n, in most cases we get close to the performance of cross-validated SVM. Now the dashed red line, that's the training time of cross-validated support vector machine. And the black dashed line, that's the time for training our method. So we achieve comparable results at much smaller computational cost. And then the blue line, that's the PAC-Bayesian bound on the prediction error of the Gibbs classifier, and you can see that in all the cases it's quite tight bound on the performance. Okay. Now to the summary. So we propose the relaxation of the PAC-based KL bound and an alternating minimization procedure for the bound. We have provided sufficient conditions for strong quasi-convexity of this function, which guarantee convergence to the global minimum. We have proposed construction of a hypothesis space, and in our experiments, rigorous minimization of the bound was competitive with cross-validation and tuning the trade-off between complexity and empirical performance. Okay? So let me emphasize this one more time. So rigorous minimization of a theoretical bound was competitive with cross-validation. Okay? What's next? So some ideas. What could be done next? So first direction is to improve the sufficient conditions for strong quasi-convexity. So again, in practice, our bound was strongly convex even when the weak separation sufficient condition was violated. And this suggests that we can probably relax the sufficient conditions. So when we did the analysis, we dropped some terms from the strong quasi-convexity theorem when we made the weak separation condition. So again, to remind you, we have bounded the variance just by this logarithmic term. We dropped the KL term. So if we take back the KL term, or if we look at the second condition, it may be possible to get weaker sufficient conditions. And another direction is to do improved analysis of the weighted majority vote and probably combine the results with improved analysis of the weighted majority vote, the C-bound that Francois has mentioned today morning. And here are some works on this C-bound that they have. So thanks for your attention.
You have time for questions?
Thanks, Yevgeny. It's really nice. I was just curious, you said you used the bound in place of cross-validation to choose between the sort of regularization, I guess. Have you also looked at using it to do some model selection in other ways? I wasn't quite clear whether you used, for instance, cross-validation in SVM to choose the width parameter as well, or whether there was any. I just wanted to get an idea of how sort of robust that is in terms of doing model selection.
Okay. Very good question. So I actually didn't get to the details of selecting parameters in SVM. So what we did for the cross-validated SVM, we did cross-validation over the width and the trade-off parameter. For our method, we have So since we had so few points, it was possible to achieve perfect separation, so we didn't have to do anything with tuning of the trade-off between the margin and the empirical error. And for the width of the bandwidth of this kernel, we have just thrown in all the same values that were used in the cross-validated SVM, which created a kind of larger base hypothesis space, and we have put all this hypothesis space into our procedure. So our procedure did complete model selection, including the bandwidth of the kernel.
Is there another question? I might have a small one. If you go back to the empirical results, just a detail, but to be sure, the bound, you said that the bound is tight, but it's the bound on the Gibbs disk, right?
It's the bound. It's a bound on the Gibbs disk, but again, the black lines are also like it's the same whether almost the same whether I take majority vote or the Gibbs prediction. In this case, yes.
Is your Gibbs in that case becomes almost deterministic?
No, not. So we had experiments on 8 different data sets, and for most of them it was more than one hypothesis that was participating in Gibbs. Not too many, but an order of 10 hypotheses for which the prior was not too small.